Today we shall consider T and F distributions. In the last lecture, we considered chi-square distribution, which was a sampling distribution from a normal population, that is derived from a normal population. T and F distributions similarly are sampling distributions that can be obtained from a normal population. We shall first consider T distribution, we will study its properties, and then we will move on to F distribution. And finally, we shall consider some numerical applications of these two distributions. Let us first consider T distribution. Let Z be a standard normal variate and chi-square be a chi-square variate with n degrees of freedom. If you can recall, earlier we said that a standard normal variate is nothing but a random variable that follows a normal distribution with mean 0 and variance unity. And we have already come across chi-square distribution, which can be seen as the sum of squares of n independent standard normal variates. We define T as Z divided by root over chi-square by n. One thing we should keep ourselves reminded that Z and chi-square have to be independently distributed. So Z divided by square root of chi-square by n, that is the degrees of freedom of the chi-square distribution. The statistic T is then said to follow a T distribution with n degrees of freedom. Now, what is the degrees of freedom of T? It is same as the degrees of freedom of the chi-square variate that we are considering. Next, we shall go into the probability density function or PDF of a chi-square distribution. You can see on your screen, it is Ft, which is equal to 1 by n to the power half b half comma n by 2. The function b, we will come to it later, we will describe it in details. Then we have 1 plus t square by n whole to the power minus n plus 1 by 2, where t lies between minus infinity and infinity. We have to understand the range of t distribution. Now see, t is defined as a chi-square variate in the denominator and a standard normal variate in the numerator. We know a standard normal variate lies between minus infinity and infinity, while a chi-square variate is always non-negative. And in the denominator, we have square root of this chi-square variate. So naturally, t will have the range from minus infinity to infinity. Now let us come to the function denoted by b. b is a beta function, and you know that beta function has got two arguments. So the first argument here is half, and the next argument is n by 2. Let us now discuss some properties of this distribution, that is T distribution. As we have already mentioned, it ranges from minus infinity to infinity. It has a bell-shaped curve and symmetric. So it is a curve which is similar to a normal distribution, and it has to be understood that the curve, the shape of the curve changes with change in the degrees of freedom of T distribution. The variance of T distribution is always greater than 1, and it is limited only to 3 or more degrees of freedom. That is, the T distribution has got degrees of freedom greater than or equal to 3. It means that this distribution has a higher dispersion than a standard normal distribution because it has got degrees more than, not less than 3. Now we come to the upper and lower alpha points of a T distribution. Now what is an upper alpha point of a T distribution? The upper alpha point we denote it by T, then within suffix alpha semicolon n of a T variate with n degrees of freedom is such a value that the right-tailed area to this value is alpha. You can see on your screen probability T greater than T alpha semicolon n is alpha. So that is, there is a point in T distribution such that the probability that T will exceed this value is alpha. By definition, it is called the upper alpha point of a T distribution. We can similarly have a lower alpha point of a T distribution. You can see on your screen the graph. It is such a value of the T distribution that the probability towards the left of it is alpha. So that means lower alpha point is such a value that probability T less than T1 minus alpha semicolon n is alpha. So T1 minus alpha semicolon n is basically the lower alpha point of a T distribution with n degrees of freedom. Now the question of notation comes in. Why T1 minus alpha? Because whenever we talk about upper alpha point or lower alpha point, we talk in terms of the right tail probability. Like in upper of alpha point, we have written T alpha semicolon n. That means probability that T will exceed this value is alpha. Now, if we talk about the lower alpha point, we are denoting it as T1 minus alpha semicolon n. Probability that T will have a value less than this is alpha. So, what is the probability that T will have a value higher than this? Clearly, it will be 1 minus alpha. So, that is the notation we always denote in terms of the right-tailed probability or the right-sided probability. Now, you see, there are some applications of T distribution. But before going into the application, since T is a symmetric distribution, we can say that the lower alpha point is minus of the upper alpha point. Now, applications of T distribution, there are several applications of T distribution, and most primarily, T distribution is applied in the case of testing of hypothesis as well as in interval estimation. When we talk about the test for the difference of two means, obviously we will come to this later, but can you think of one problem where we can have the test of the difference of two means? So what can be a testing problem for testing the difference between two means? We can think of a practical example. Suppose there are two localities. We may feel like testing whether the average income of the persons living in locality A and that of locality B are equal. So that means we are testing for two means. Now this testing may be done in two different situations. It may be that the variances of the two groups of individuals are same, that is the variance of income of the two groups of individuals are same, or the variances may not be same. In either of the two situations, we can make use of T distribution. Now, the testing of difference of means for two populations may be thought of as independent populations or they may be dependent populations. That means the two populations that we are talking of, they may be unrelated or they may be related in some respect. In either of the two situations also, we can use T distribution. We can think of the testing about the correlation coefficient. Testing about the correlation coefficient may be something like this. Sometimes we may say that production of paddy depends on rainfall. So to what extent production of paddy depends on rainfall? That question may arise. That means where there is a non-negative correlation between production of paddy and rainfall. That one may feel like. Now here also we may have positive correlation, we may have negative correlation, we may have zero correlation. That means the population correlation coefficient may be zero, may be positive, may be negative. That is, we can distinctly identify two situations where the population coefficient rho is 0 and when it is non-zero. For such testing also, we can use T distribution. So you can see there are several applications of T distribution and it is really a very important distribution in case of statistical inference or in particular testing of hypothesis. Now we shall come to F distribution. Suppose we have two chi-square variate, chi1 square and chi2 square. Chi1 square is a chi-square variate with n degrees of freedom or n1 degrees of freedom, let us say, and chi2 square is also a chi-square variate with n2 degrees of freedom. We shall further assume that chi1 square and chi2 square are independently distributed. Now we define something called F. It's a statistic, F statistic, which is equal to chi1 square by n1, the whole thing divided by chi2 square by n2. More specifically, chi1 square divided by its degrees of freedom, the whole thing divided by, in the denominator, chi2 square by its degrees of freedom. F is then said to follow an F distribution with degrees of freedom n1, n2. Now mind you, unlike chi-square and T distributions, F has got 2 degrees of freedom, n1 and n2. What is n1? The degrees of freedom of the chi-square in the numerator, and n2 is nothing but the degrees of freedom of chi-square in the denominator. So we write, as you can see in the slide, F has got the degrees of freedom n1, n2 within first bracket or parenthesis. Now we come to the probability density function or PDF of a F distribution with degrees of freedom n1, n2. We'll always say like this, degrees of freedom n1, n2 for F distribution. So you can see the PDF is something like this, n1 by n2, this whole thing to the power n1 by 2 divided by again beta function n1 by 2 comma n2 by 2, f to the power n1 by 2 minus 1, then 1 plus n1 by n2 into f whole to the power minus n1 plus n2 by 2. Quite a complicated PDF. I'll say that you need not remember this PDF very well, but it's better to know this PDF. More importantly, the range of F distribution. Now, what is the range of chi-square distribution? We already know that the range of chi-square distribution is from 0 to infinity. So, in the numerator, we have a quantity which lies between 0 and infinity. Similarly, in the denominator. So, the ratio will definitely lie between 0 and infinity. So, F distribution ranges from 0 to infinity. That we have to remember. F distribution is positively skewed. Unlike T distribution and standard normal distribution, F distribution is positively skewed. If you can recall, we have said that chi-square distribution is also positively skewed. So similarly, F distribution is also positively skewed. And it has got degrees of freedom n1, n2 as we have said. And as we increase the degrees of freedom, we can see that the skewness will go on decreasing. The value of F distribution is always positive or 0, since the variances are the squares of the deviations, and hence it cannot be negative. So once again we can justify the fact that F statistic or F distribution lies between 0 and infinity. The shape of F distribution, that is not only skewness, also to some extent kurtosis, will depend on the parameters n1 and n2, which are the degrees of freedom. So mind you, in F distribution, we have only two unknown statistics involved in the PDF, n1 and n2. And as we have mentioned earlier, that these unknown statistics are called parameters. So here, n1 and n2 are the two parameters of F distribution. The values of the area lying on the left-hand side of the distribution can be found out by taking the reciprocal of F values corresponding to the right-hand side, and the degrees of freedom in the numerator and the denominator are interchanged. This is a very important property that we will come later also. This is called the reciprocal property of F distribution. So reciprocal property in details. Symbolically, we can represent this as f1 minus alpha n1 n2 is equal to 1 by f alpha n2 n1. It is a very important property. In T distribution just now, we talked about upper alpha point and lower alpha point. Similarly, in F distribution, we can have upper alpha point and lower alpha point. So this property will enable us to express the lower alpha point in terms of the upper alpha point. Only the degrees of freedom will get interchanged and the thing will be taken in reciprocal. So that is why it is called the reciprocal property of F distribution. Now, when this property is used, it is mainly used in situations when the values of the lower tail F values are to be determined corresponding to the upper tail F values. So that means lower tail F values are to be obtained in terms of the upper tail F values. Then this property comes very handy. Thus, there are properties of F distribution that tells us how the sample is distributed under study and what statistical inferences can be drawn from them. So these properties are very important in this situation because ultimately we are studying sampling distribution. So we have to understand the sample characteristic. That means we have to understand how the sample observations are varying. So these properties will enable us to study the sample carefully and then to draw justified conclusion about the population characteristics. We now come to the upper alpha and lower alpha points of F distribution in details. Similar to the F distribution, it is such a point that the probability to the right-hand side of it is alpha. Similarly to T distribution, the only difference is that T has got 1 degrees of freedom as we mentioned earlier, but F has got 2 degrees of freedom. So it is denoted as you can see on your screen, F alpha n1 n2, and probability that F will be greater than F alpha n1 n2 is equal to alpha. Similarly, one can define the lower alpha point of a F distribution. It is such a value that probability F less than that value is alpha. Now we denote it by f1 minus alpha n1 n2. As I mentioned, in case of T distribution, the notation of the lower alpha point is in terms of the right tail probability. So in case of lower alpha point of the F distribution as well, the probability to the left hand side of it is alpha. So the probability that it will be greater than this value will be 1 minus alpha. So we denote it as f1 minus alpha n1 n2. That is written in the second line. You can see if probability F greater than f1 minus alpha n1 n2 is equal to 1 minus alpha. Now again we will come back to the reciprocal property that f1 minus alpha n1 n2 is equal to 1 by f alpha into n1. We can see when we will apply F distribution in particular sums, in testing of hypothesis, in interval estimation, we will require both upper alpha and lower alpha points. Right. Now the reciprocal property of F distribution enables us to express the lower alpha point in terms of the upper alpha point. This is simply because in F distribution table, which was primarily given in Biometrica tables volume 2, the lower alpha points have not been tabulated because of this property. Similarly, in case of T distribution, we had lower alpha point is equal to minus of upper alpha point because T distribution was symmetric. Now we have seen that F distribution is positively skewed, so the lower alpha point cannot be written as the negative of the upper alpha point, but we have this reciprocal property of the F distribution which will enable us to express lower alpha point in terms of upper alpha point. We have several applications of F distribution. Testing the equality of variances of two normal populations. When we talked about T distribution, we talked about test for difference of means. In the same way, we can test for difference of variances, whether the incomes of one population is more variable than the incomes of the other population. In other words, we talk of the term consistency. We can think of testing whether the income of one population is more consistent than the other population. This is the other word for variance, consistency, looking at from a different perspective. Testing the equality of means of k normal populations. Can you think of an example where we have to test for equality of means of several populations, not of two populations, but of several populations? Can you think of such a practical example? Now see, testing for the equality of means of several populations. When can it come in practice? Suppose we are growing paddy in a number of fields in different localities. We may want to test whether the average yield is same in all the fields of different locality. That means we are testing for means of several populations. Actually, testing for means for several populations is called analysis of variance. But there is one assumption that we have to follow in analysis of variance, that is, the populations are normal populations. That means if I say there are k different fields and we are growing paddy in k different fields, now there may be several factors affecting these fields in terms of fertility, in terms of pesticides that we may use. So in all these respects, the fields may vary from one another, but we may feel like testing whether the mean yield or the average yield of paddy in these fields are equal or not. In this case, we use a F distribution, or to be specific, an F test. This is basically analysis of one-way classified data. Similarly, one can have analysis of variance for two-way classified data. There may be fields which are deviated or which are separated by two factors. One may be fertility, there may be a river flowing and the fields are at different distances from the river, so the fertility will vary. And the other may be, we may apply different pesticides to these fields. So again the yield will vary according to the use of pesticides. So that means ultimately the yield will vary according to the use of pesticides and the fertility. That means with respect to two criteria. This is called analysis of two-way classified data or analysis of variance of two-way classified data. In this case also, F statistic plays a very important role. So F has got very nice applications that we have to understand. Now we come to a very, very important result. We have to remember this result because in later lectures we will use this result. Let x1, x2, xn be identically and independently distributed random samples drawn from a normal mu sigma square distribution. Now let me clarify the terms identically and independently distributed. First, identically. x1, x2, xn are random variables. They are identically distributed means each of them will have the same probability distribution. To be specific, each of them have the same probability distribution function, same PDF. and they are independently distributed. That means there is no relation between one another. And here we are assuming that each of these random variables will follow a normal mu sigma square distribution. We define the sample mean x bar 1 by n summation xi and s square 1 by n minus 1 summation xi minus x bar whole square as the sample variance. I know that earlier you have learned the formula of variance as 1 by n summation xi minus x bar whole square, but believe me that we will use this formula of sample variance, that is instead of 1 by n we will have 1 by n minus 1. I will justify this in my subsequent lectures, why I am taking 1 by n minus 1. Now, x bar can be shown to be follow a normal distribution with mean mu and variance sigma square by n, while n minus 1 s square by sigma square may be shown to be follow a chi-square distribution with n minus 1 degrees of freedom. Also, x bar and s square are independently distributed. That means, in a nutshell, what we want to say by this result? If we have a random sample drawn from a normal mu sigma square population, we define x bar as a sample mean and s square as a sample variance. X bar will follow normal mu comma sigma square by n, while n minus 1 s square by sigma square will follow a chi-square distribution with n minus 1 degrees of freedom. And x bar and s square are independently distributed. This is a very important result, and we will apply this result in several situations, as we will be able to see in the subsequent lectures. Now, we shall come to some numerical examples of chi-square T and F distribution. In the last lecture, I did not take up the numerical example of chi-square distribution because if we consider the three distributions together, then it will be easier for us to understand and appreciate the application of the three distributions. The first one, if xk, k running from 1 to 3, that is what I am meaning, x1, x2 and x3 are independently distributed normal variables with mean k and variance k square. The problem is to construct a chi-square distribution with 3 degrees of freedom using x1, x2 and x3. I'd like to remind you that a chi-square distribution is nothing but the sum of squares of n independent standard normal variates. Now here we have 3 independently distributed normal variates which are not standard normal with mean k and variance k square. So in particular, x1 will follow normal 1, 1 square, x2 will follow normal 2, 2 square, and x3 will follow normal 3, 3 square by the problem. Also, we are given x1, x2 and x3 are independently distributed. So, can you construct 3 standard normal variates out of x1, x2 and x3? So, from x1, x2 and x3, we construct 3 standard normal variates y1, y2, y3. We'll subtract the mean and divide by the standard deviation. So y1 will be x1 minus 1 by 1, y2 will be x2 minus 2 by 2, and y3 will be x3 minus 3 by 3. So now in our hand we have 3 standard normal variates. So as you can recall, a chi-square distribution is nothing but the sum of squares of standard normal variates. So we take y1 square plus y2 square plus y3 square as a chi-square variate with 3 degrees of freedom. So that completes the answer. We go to the next problem. x1, x2 up to x5 are independent normal variates with mean 0 and variance 1. That means x1, x2, x5 are independent standard normal variates. We have to determine the constant k such that the random variable given by k into x1 plus x2 divided by root over x3 square plus x4 square plus x5 square will follow a t distribution. Now, to solve such problems, I would ask you to remember the definition. What is the definition of a t distribution? Let me remind you. In the numerator, we have a standard normal variate, and in the denominator, we have square root of a chi-square variate divided by its degrees of freedom. Simple. So, x1 follows normal 0, 1, x2 follows normal 0, 1, x1 and x2 are independent. So, if we use the additive property of normal distribution, we can say that x1 plus x2 will follow a normal distribution with mean 0 and variance 2. So, clearly, if we define z as x1 plus x2 minus 0 or simply x1 plus x2 divided by root 2, it will follow a standard normal distribution. So we keep the standard normal distribution in the numerator. Now in the denominator, we have construct a chi-square variate. See, we have x3, x4 and x5, we are standard normal. So x3 square plus x4 square plus x5 square will follow a chi-square variate with 3 degrees of freedom. So in the denominator, we will keep square root of x3 square plus x4 square plus x5 square divided by 3. So ultimately we have x1 plus x2 by 2 divided by root over x3 square plus x4 square plus x5 square by 3. So the constant will come out as root over 3 by 2. Now we will come to our final example or final application. x1, x2, x3 and x4 are independently distributed normal variate with mean 0 and variance is a unity. That means they are standard normal variates. The question is, what is the distribution of 3x1 square divided by x2 square plus x3 square plus x4 square? Now see, here we don't have x1, we don't have any square root. That means we nullify t distribution, we nullify chi-square distribution. But we have a ratio when in the numerator we have one squared quantity, in the denominator also we have squared quantity. That means the only option is to go for F distribution. Now clearly, since x1 follows normal 0, 1, so x1 square will follow a chi-square distribution with 1 degrees of freedom. Similarly, as we have seen in the earlier situations, x2 square plus x3 square plus x4 square, this being the sum of squares of 3 independent standard normal variates, will again follow a chi-square distribution with 3 degrees of freedom. Now we take x1 square by 1 divided by, in the denominator, x2 square plus x3 square plus x4 square by 3. So that means we have one chi-square distribution with 1 degree of freedom by 1 in the numerator, and in the denominator we have chi-square with 3 degrees of freedom by 3. So this will follow an F distribution with degrees of freedom 1, 3. So these are some of the applications of F distribution. Now in the subsequent sections we will start with theory of statistical inference, where we shall apply these sampling distributions in details. Thank you.